So throw this way. Okay, so I know you've seen this, but this is a beautiful thing. Good. Okay, degree distribution is a big deal. Now, we have to be careful about this. This is a very important thing, right? So of course we're just choosing nodes, right? So we're going to our network or our ensemble of networks. We're choosing a node and looking at how many friends it has. When we think about spreading, and a lot of mechanics on networks, we really need to be looking at edges. And so we need to start thinking about what happens if we jump on a random edge and then randomly run along in one direction, right? And we hit a node. What's the number of friends or the degree of that node going to be like? All right, so this is a real cornerstone of a lot of work that comes afterwards. So we need to understand it. So we'll have P, Q, and R, right? So Q is going to be probably the node at the end of a randomly chosen edge has degree K, right? So we go to our network, we jump on an edge, and then we randomly choose it, flip a coin, we go this way, we hit a node, probably that has degree K, which includes the edge you're on, is going to be QK. And so this is an easy thing to derive from PK. It has to be proportional to, we'll probably find a node of degree K, but there are K ways to get to it, right? Right. So if you think of your network, every node that has degree 3, now there are 3, it's going to be sampled threefold the rate that it would have been if you just sampled nodes, right? If you have a degree 30, there are 30 ways to get to that thing, so it's going to be 30 times what it was. So there's this linear piece that just pushes it up, and really beautifully, turns out to be the rich get richer phenomenon, right? So this works for provides the mechanism for scale-free network growth, or any of those sort of adjacent ones, because you can go and meet someone in a network, and then you start to meet their friends, and their friends will be different, right? Their friends will have more friends, and this is going to be right. We're going to take this degree distribution P sub K and then push it across a little bit because we're going to multiply it by K, so it's going to have a higher average degree. If we normalize it, simply divide, right? Sum over. That's all this is. We're summing over this blob and dividing through, so that's our normalization. And if you look at the thing on the bottom, this, of course, is just the average degree, right? So you can write in that way. So people often do that. Average degree on the bottom. All right. So, as I said, the rich get richer mechanism is just built into this selection process. It's just there for free. The work by Redner, I should go through that probably. Redner and Krapivsky, where they looked at K to a power. It's certainly a thing you can play around with, but it doesn't have a simple story like this. All right, very nice. And so this is an explanation of these things, right? So this degree 6 one is going to probably have been 1 over 7 if you're just choosing by nodes. But now if we go to edges, and you can think of breaking it all up and then choosing stubs, right? Now it's got 6 ways of being chosen. Of course, there were 8 edges in this thing, so there are 16 stubs, so there are 6 divided by 16. That's the probability of getting to 6 divided by 16 is probability of getting this guy. So that's this thing here. Now we're going to, for convenience, it's often useful to talk about what's the probability that node you run into has K other friends, right? This is just a simple shift, K other friends. And so that's going to be the R distribution. So it's the same as the Q distribution, but everything's been shifted, right? So the probability that we hit, so there are these guys, 1, 2, 3 here that have degree 1. So there's a 3 on 16 chance we get to one of those if we go along an edge. That's going to match up with R0, 3/16. R0 is the chance that we hit a node that has 0 other friends. And this one has 0 other friends. This one, we come in here, it has 5 other friends, right? So Q6 goes to R5, Q2 goes to R1, and Q3 goes to R2. That's all, just a little shift. It's just useful in some calculations. And you see it in the literature. So is that okay? So these are amplifications, right? 6/16, certainly, considerably greater than 1/7. So its standing has gone up if we think about this. All right, I think we can get through this piece. So, yeah. As was on the previous page, right? All these things. So you can just write it down. You want to say, probably that someone has 7 friends is probably that they have 8 friends, and because you want 7 other friends, I should say, is the probably that you hit a node that has 8 friends. Fine. So it can be written out in the same way, or just a shift from the QK one. So then you talk about this, what's the expected number of friends? And this is this kind of somewhat famous thing now. I guess there's some, I mean, it depends if the network is weighted and all sorts of stuff like that. But the basic story for a flat network is clear. So we're going to use this notation. What's the average number of other friends that a randomly arrived at node has? So this is just normal distribution stuff, right? We're just trying to find the average of k with respect to this distribution R sub k. We'll put that in terms of pk itself. Yep. Okay, we're going to stuff this thing in, right? So again, right, it's the chance that you run into a node that has one more friend than the one we're thinking about. And the average degree that's just going to come out, that's here. There's a k equals 0 piece, so we can shift this. We'll make it k equals 1 on the subscript, or the index will start at 1. And then we have this little beast here, right, k plus 1. And if we want to do the right thing, right, so you can play around with this in different ways. You could see this as, that's okay. I guess we could just do that. Why have I done that? Okay. Yeah, so the issue is this is a pk plus 1, right? So if we're going to return something where we have means and variances in terms of the underlying degree distribution, right? We're trying to tie everything back to the underlying degree distribution. Then this k plus 1 is what we need to connect with. So this is good, but this is a k, so we can make that k plus 1 minus 1. That's what's happening here. Right, so we made it k plus 1 minus 1, right? This is still k times k plus 1. And then that's equal to k plus 1 squared minus k plus 1. Right, so it's just a little bit of just doing things clearly. We want to make all the things the same. Yes, often what we do in math, make all the things the same. And that's pretty good. And so we're going to shift let me clean that up later on, because there's something a bit not great about that, right? What am I doing wrong with this? So this is, what am I doing? What? No? Crazy person. I didn't need to do that. Yeah?
You just added in, like, j equals 0 goes away. J equals 1 is without some.
That's all good, right? J equals 0, yeah. Right?
J equals 1 is kp plus 1 would equal 2, which is
0 and 1 go away. So we're still good. Yeah, all right. So I didn't, because this would have been k equals 2,
yeah.
and then I just moved it down. Yeah. Yeah. It was just nice, just, okay, so, and then when it's back to j equals 0, then we're good, right? This really should be j equals 2, but of course we can shift it back to, so, yeah, okay. it's just, that wasn't very nice. Okay, so we have, what do we have? We have a j squared and a j, pj, so this is going to be the second moment minus the first moment. And we have this beast out the front. Okay, so I've just repeated up there. It's true for all random networks. This is not about degree distribution. For the standard random networks, then we have this piece, right? So we had this kind of, this is for Poisson degree distribution. We had the second moment is the first moment squared plus the first moment. So if we stick that in, we get this kind of funny result. So we're just going to stick it in here. This is the second moment. We're stuffing that in here. These things cancel. This cancels here. We get the mean back, right? So if you run along an edge in a Poisson degree distribution, degree distributed network, then you hit a node. It will have, on average, the number of other friends we'll have will be the same as the number of friends that a randomly chosen node will have. And that's it. So that it's, right, so they'll have one more, right? So your friends will have one more friend than you on average, which is fine. But it just, because it's so tightly connected, you know, it's so cleanly connected, it can lead to some little mistakes in calculations, actually. Right, that's a property of this guy. So yes. Okay, so this is a special thing. I'm just going to get rid of this. Let's not worry about that. That's fine. So in fact, you know, really what's happening is R sub k is equal to P sub k if you go through it. It's not just the average quantity. It's really the same.